Welcome to the first lecture on the Internet of Things at Karlstads University. So, in this lecture today, we're going to give you an introduction to the topic of the Internet of Things. We'll give you an overview, and we'll start digging into it with a discussion of the history of the Internet of Things. So, my name is Michael Engel. I'm the teacher for this course this semester. So, if you have any questions, just feel free to get in touch. So, let's jump right in, and we'll jump back around 50 years to the beginning of microprocessor technology. So microprocessor technology and integrated circuits are some of the very basic things that enable the Internet of Things. So the very first microprocessor was the Intel 4004, which was introduced more than 50 years ago. And this was a very, very humble chip. So it only had 4 bits of data width, so it could only calculate on numbers between 0 and 15 and one operation. And it was pretty slow, so it ran at 500 to 700 kilohertz. But nevertheless, it was the first commercially produced microprocessor, and that was already produced and intended to be used in what we would today consider an embedded systems application, a desktop calculator. And of course, many companies jumped on that bandwagon, and there were lots of developments. So around 10 years later, we had quite some progress in this area. So we had another system called the Intel 8051. This is an 8-bit microprocessor, but it includes more than the processor. So it seems to run significantly faster. So it runs at 12 megahertz. So it's still a pretty slow machine. And this Intel 8051 already included memory on chip, and that was pretty new back then. So you had 128 bytes of RAM. That's not a lot. And 4 kilobytes of ROM. So usually back then, your programs were quite a bit larger than the amount of data you had to operate on. So this worked pretty well, and it was relatively cheap. And amazingly, the Intel 8051, 40 years later, is still shipping billions of units every year. So if you have for example, Bluetooth controller in some of your embedded and IoT devices, you wouldn't be too surprised to find some sort of 8051 in there. So you can see both chips on the right-hand side. So the Intel 4004 is pretty small, so it only has a 16-pin package, whereas the Intel 8051 has a 40-pin package. So it includes much more functionality. And in addition to the RAM and ROM and the microprocessor itself, the 8051 had some improvements in terms of peripherals. So you also could communicate with external devices directly without requiring additional ICs. So what this means is you could build a single chip solutions for embedded systems. This 8051 chip was all you needed. Still, the 8051 was a bit cumbersome, and for many years people thought you could only program it in assembly language, and of course people wanted to use higher level languages. And so this area of what we now call microcontrollers, because they don't only include a microprocessor, but additional peripherals and the memory. So there were additional developments here. And one important development you've probably seen before is by a company called Atmel, which was bought by Microchip a couple of years ago. And this is the AVR microcontroller family. This is still an 8-bit microcontroller family. It was developed since 1969. It's quite a bit faster than the 8051. It runs up to 24 megahertz. It has very many different models, which start at very small amounts of RAM, 64 bytes for very small and cheap applications. But you can get controllers with RAM up to 16 kilobytes. And you've probably seen the Arduino boards before, so the AVR microcontrollers are used as the basis of the Arduino boards. And it's a very simple, what we call a RISC architecture, a reduced instruction set computer like the ARM processors you know nowadays. And amazingly, it has been developed as a master thesis of 2 students at NTNU in Trondheim. And these 2 students are, of course, now important businessmen, and they're still working in industry, consulting, and running their companies. So this is pretty interesting. But still, we're very much restricted here because we are running on 8-bit devices. So working with larger numbers, working with floating point numbers is pretty cumbersome. The ATML AVR could, however, be programmed and was usually programmed in C, so you could use a high-level language, and there are even implementations like MicroPython available for it. Nevertheless, the functionality required in embedded devices is always increasing, so the next logical step is actually to increase the computing power we have available here. And so in very many of today's systems, you can find a 32-bit processor nowadays, especially when it comes to things important for the IoT, like wireless communication using Wi-Fi or Bluetooth or mobile communication. When it comes to on-device picture, video, or audio processing, you need more compute power than what is available in the 8-bit chips, and especially you also need more memory for most of these. So the norm today is that in very many devices you will find a processor or a microcontroller based on a processor by a formerly British company called ARM. And this is a 32-bit microprocessor. And the original ARM CPU is also already more than 30 years old. It was originally intended for a set of desktop computers by a company called Acorn. So that's why ARM originally stood for Acorn, RISC machine. And the important thing, which was not intended when ARM was invented, is that ARM turned out to be very, very energy efficient. So ideal for use in mobile, portable, battery-driven operations. So nowadays you can mostly find 3 different processor families provided by ARM, and ARM itself doesn't produce any chips. So it just licenses what we call the intellectual property. So they, in some respect, the blueprints for a microprocessor or microcontroller. And there are lots of companies out there like STMicro, NXP, Texas Instruments, and of course many companies in Asia, many more around the world, producing their own microcontrollers based on one of these blueprints available from ARM. Of course, they have to pay for it. So the smallest ones are the Cortex-M series, the microcontroller series, and these are the ones we're going to take a closer look at in some of the upcoming lectures. There's a special version of the Cortex-M, which is a bit more powerful. This is the Cortex-R series for real-time controllers, which is often used in real-time critical applications like, for example, cars. And you've probably already used the device with a Cortex-A processor. So A are the application processors, which are commonly found in mobile phones, tablets, but you can also find them in laptops like some Chromebooks or the new Apple MacBook series with the M1 chip nowadays. So, by the way, of course, if you look at the 3 letters identifying the CPUs, they neatly make up ARM for ARM. One example using ARM processors, which is often used in IoT devices, is the Nordic Semiconductor NRF 52840. This is around 5 years old, and this has a Cortex-M processor of the Cortex-M4 variety running at 64 megahertz. This not only has a 32-bit integer unit, it can also process floating point numbers, and it has quite a lot of memory for an embedded device. So it has a whole megabyte of flash ROM memory and 256 kilobytes of RAM. And in addition, because it's a microcontroller, there's lots of peripherals, and Nordic Semiconductor includes peripherals which are very interesting and very important for the IoT. So it can run Bluetooth Low Energy, Bluetooth Mesh protocols, NFC communication, and the Thread and ZigBee protocols supported by a software development kit, which can make use of the very flexible radio hardware that's developed by Nordic Semiconductor. So, how have we been able to achieve all this progress over the last 50 years? Now, one of the important drivers of this progress is an observation by one of the pioneers of semiconductor, Gordon Moore. And Gordon Moore already observed in 1965 that the number of transistors in a dense integrated circuit, so in a today's silicon-based integrated chip, doubles about every 2 years. So Gordon Moore was the later CEO of Intel, so I guess he knows what he's speaking about. So this is not a law like a law, from physics. This is just an observation and an empirical relationship, but it has worked out quite well for the last couple of decades. So this empirical relationship that was observed is linked to gains from the experience in production. So your production was more reliable, it could use new technologies, and you can see the development that took place here on the right-hand side in this graph. So we have this exponential growth in the number of transistors available on a chip for almost the last 50 years. And the reason for this was that we were able to shrink the structure sizes, so the smallest elements we can put on a silicon chip, significantly. So the Intel 4004 in 1971 had 10 micrometer or 10,000 nanometer structure sizes. The NRF 52840 we just talked about 5 years ago is in a relative conservative process, so it's running on 55 nanometers. But as you can remember, as you can figure out, that's almost 200 times smaller. And remember, we're building in an area, so the number of transistors goes up significantly more. And the current chips like the Apple M1, which was introduced in 2020, is running on 5 nanometers. So smaller structure sizes means we have more transistors per silicon area. So in turn, this means we have a lower cost of semiconductors. So we can nowadays obtain chips like microcontrollers for a few cents. So this means, in turn, for IoT applications, that we can afford to put a microcontroller in almost any device because it doesn't increase the cost significantly compared to all the other costs when developing a device. Now, another thing that's important is that the power consumption is not allowed to go up when we scale the number of transistors significantly. So the other law, so to say, or observation that is important here is so-called Dennard scaling. So Dennard scaling is another observation which is especially important for energy-critical battery-operated devices. And this scaling law says as transistors get smaller, their power density stays constant, so the power use stays in proportion with the area. So we're shrinking down the structure sizes of our semiconductors, so our transistors get smaller and smaller, and the energy they use, or the power they use in this term, not the energy, is also shrinking accordingly. So that means the smaller you can build your structures on a chip, the less power hungry they are, so you can afford to run a much larger number of transistors on the same power budget as before, or you can run the same number of transistors on a much lower power budget if you scale them down in size. In addition, we can scale the voltage, and if we scale voltage and current downward with the semiconductor structure length, we can create energy-efficient devices that can run on batteries for hours and hours. There is one problem. And this problem is we're hitting physical limits. So Moore's law is in the 1-digit nanometer scale. So these semiconductor scales are around the size of 30 to 50 atom diameters of silicon atoms. So of course, silicon is the basis for everything, and you can't scale much further down. So people expect we can scale down to 4, maybe 3 nanometers, but we might need a technological breakthrough to go much further down. So this is a significant problem that, probably precludes us from including more and more transistors. But also Dennard scaling hits the physical limits. So in a real physical device, you have two sources of power consumption. So this dynamic power consumption is the power we use when we're switching a transistor. So when we switch a value in a digital circuit from 0 to 1 or the other way around. So we have to move around charges, so we have to switch capacitance, and this just is what creates the power consumption. Now, the problem is that there's another source of power consumption, which is the so-called static power consumption or leak currents. So these are all the currents that flow where you don't want them to flow, but you can't avoid it because you can't build a perfect insulator on chip. So this static power consumption was usually very low compared to the dynamic power consumption that was behaving according to Dennard scaling. But in modern circuits, actually static power consumption is the more significant part, and static power consumption is not decreasing in the same way with Dennard scaling. So we cannot put more transistors on chip, and even if we made them smaller, we would not be able to save energy again by making them smaller. So in turn, we need new approaches to scaling and energy efficiency if we want to make these chips even more complex than they are today. But nevertheless, with the technology available today, we can already build very, very efficient, small, and still powerful embedded devices as the basis of IoT applications. So the consequence of these 50 years of development is that computers are everywhere, especially tiny computers. So the progression of Moore's law enables increasing functionality and speed and energy consumption going down due to Dennard scaling, and in turn, we were able to lower the prices of processors significantly. So, for example, the first computer built by Apple in 1976 used what was then considered a low-cost microprocessor. So this was a 6502 by a company called MOS Technology, and this cost $25. And that was a bargain because an Intel processor cost like 10 times as much. Nowadays, you can find very obscure microcontrollers, but still perfectly fine microcontrollers from especially Chinese companies that cost as little as 3 cents per piece. So prices have gone down, so it's not a problem to put a microprocessor or a microcontroller in any sort of device, so to replace embedded, dedicated hardware for controlling things by a piece of software running on a microcontroller. And this is what drove innovation in this research and industrial area we call embedded systems. So what's an embedded system? Well, there are many definitions of embedded systems. One by my former boss, Peter Marwedel in Dortmund, is quite nice. So embedded systems are information processing systems, and they're called embedded systems because they're embedded into an enclosing product. So what's important for an embedded system is that it's just part of a larger thing. If it's a car or a refrigerator or a mobile phone, so these are all embedded systems. If you want to learn more about the embedded systems background, we're going to discuss some of these things later on in this course, and you can dig deeper in the literature reference here, number 5 that's referenced. That's our book on embedded systems, foundations of embedded systems for IoT and cyber physical systems. This is freely available as a PDF download from Springer, the publisher website. The other important development is in networking. So networking, and especially wireless networking, proliferated starting in the late 1990s. So we first had protocols like IEEE 802.11, which you probably know better as Wi-Fi or wireless LAN. We had Bluetooth, and this was also made possible due to the availability of highly integrated semiconductors, so complex semiconductors that were able to handle radio, communication, protocols, everything that mostly was not analog. And more recent chips also include lots of the analog parts of a radio for wireless communication. So here's an example how many embedded devices can be found. So this is a modern car. And a modern high-end car now uses more than 100 different microcontrollers, 100 different embedded devices. In cars, they're called ECUs, embedded control units. And these are all networked, so they have to operate together. So when you hit your brake pedal, you are not only able to enable your brakes, but also the brake lights should go on. Your ABS system should be able to react, and so on. And there are different networking standards. Most of them in a car today are wired, but increasingly you can also find wireless standards in cars. So cars using Wi-Fi, cars using 3G, 4G, 5G communication, for example, to alert the authorities when you're in an accident, stuff like that. So a modern car nowadays is full of computers. All these computers use energy, which is especially a problem in electric cars because energy or electric energy is not just a byproduct of running a combustion engine, but your motors and your computers have to compete for all the energy all the time. And of course, it's a problem because someone has to develop all the software. So There's an estimate that more than half of the development cost of a car is now not in mechanical components, but it's in electronics, embedded systems, and especially software for a car. And you've all seen these news like new cars coming out, but they're delivered with a better firmware because the mechanical parts were ready, but the software engineers were not ready actually writing the software. So you had to go to your garage to get a software upgrade every now and then to fix bugs or to add some features. Now, how do we get to the IoT? We've mostly talked about embedded systems and the hardware developments that enabled embedded systems. Now, the first ideas of using embedded systems to actually include them in our everyday life were done at a research lab by a company called Xerox. You mostly probably know from photocopiers, but Xerox is a very innovative company. So in their so-called Park research labs, they invented a lot of things, including the graphical user interface and the mouse by Doug Engelbart, Ethernet networks by Bob Metcalfe and his colleagues, the laser printer, the personal computer, electronic paper, and many more things. Unfortunately, Xerox was unable to make a product out of most of them, so the graphical user interfaces were then taken up first by Apple and then by Microsoft, obviously, which gave us Mac OS and Windows. Ethernet networks were commercialized by Bob Metcalfe and a company founded called 3Com, and then now you have, of course, lots and lots of companies building Ethernet products, and so on. Nevertheless, they were always able to hire excellent academics, and one of them was Mark Weiser. So in 1991, Mark Weiser worked at Park, and he started to think about like what should the computer for the then next century, so the century we're living in, the 21st century, actually look like, and he formulated his vision. So his vision was that the computer for the 21st century would have specialized elements of hardware and software, and these would be connected by wires, radio waves, or infrared, and all these specialized elements of hardware and software will be ubiquitous, and they will be so ubiquitous that no one will notice their presence. So you don't have a computer that's sitting on your desk or on your lap or somewhere, but it's just hiding away somewhere, just doing a task without you noticing, and it will feel natural for you to just have computer support somewhere in your environment. And this development is a direct consequence of the progress of Moore's law and Dennard scaling, and Mark Weiser was so innovative to actually foresee this development with technologies that were only available in the early 1990s. So he actually started to define some principles for ubiquitous computing, and some of those, like number one and three, we're going to discuss, were focused on the human interaction with computers, and the large invisible part of what we now call the IoT infrastructure is better captured in numbers two and four. So these principles include first, the purpose of a computer is to help you do something else. So a computer is not a purpose in itself, but you just use it as a tool, like you use a screwdriver or a hammer or something like that. It just can do much more complex tasks than a screwdriver can do. Number two is the best computer is a quiet, invisible servant. So it shouldn't take your attention away from the things you're going to do. It should just react. It should probably react predictably and, of course, reliably. Number three is the more you can do by intuition, the smarter you are. The computer should extend your unconscious. So essentially, you should be able to use a computer maybe like you use one of your limbs, so you don't have to start thinking about how you use a key to unlock your door, and maybe a computer should work the same way so that it feels natural as an extension of your capabilities instead of something you have to work a lot to get something done, to have to think a lot to get something done. And number four is a bit strange. It sounds like technology should create calm. So, what's calm? So, there's a paper on this also, and Weiser and his colleague John Seeley Brown uh, describe calm technology in their paper, Designing Calm Technology, as that which informs but doesn't demand our focus or attention. Now, if you look at computers today, especially your mobile phone, which beeps and rings all the time because you get a new message, I'm not sure if that vision has worked out, but yeah, it was one part of the vision that the computer should integrate, should be in the background instead of just driving away and capturing your attention. So this leads us to what we call the post-PC or post-personal computer era. So in general, we can observe three generations of computing. So in the very early days of computing, we had mainframes. So we had one very big, very expensive, loud and power-consuming computer. And since these computers were big and loud and power consuming, you had to have many users use this computer because otherwise you just couldn't afford to spend $1 million on just a computer for a single person. Then, starting in the late 1970s, desktop computing came in. So prices have gone down. We have cheap microprocessors available. So this enabled us to have one computer per user. And phase number three, as you can see, is what we call ubiquitous computing now. So we can afford to have many computers per user, and most of these computers you actually never recognize as computers because there might be a computer in your set of headphones. There's even a small microcontroller and an electric toothbrush where you wouldn't expect it, maybe. So essentially, you have many computers, but if you would have to administer all these computers, you would be busy all day. So essentially, most of these computers should just run in the background, do their tasks, maybe just simple tasks, do them efficiently without requiring your attention. So when we talk about the history of the IoT, I thought it would be interesting to discuss some of the early ubiquitous devices. So some research was done at a joint research lab in the UK by Olivetti and the US phone company AT&T. And this was a very simple technology called the active badges. So the researchers here were concerned with the problem of people moving around in a large office building. And this, remember, was in an era where mobile phones and mobile phone networks were not ubiquitous. So essentially, when you wanted to reach a person, you called this person's desktop phone number. And when that person was not at his desk or her desk, then you had trouble reaching that person. The same with computers. You sent an email to that person. It was available at the desktop computer in that person's office. But if that person was like 3 floors down in another department, some urgent stuff could not be delivered. Now, these badges try to solve the problems. So these badges were just sending information unidirectional, so they emit a wireless signal. Now, wireless today mostly means radio. Back then, technology was very primitive in comparison to today. So these active badges used infrared light instead. So more or less the same you use in your TV remote nowadays. And they did this periodically every 15 seconds. So essentially, if you had receivers spread around your building in every office, then you could actually figure out which badge was in which room. And of course, if the badge owner was wearing the badge, then you could figure out where the owner was. And this enabled functionality like what they call teleporting. So the computers were networked, but only by wired networks, so Ethernet mostly. So you could sit down at any computer in the office building and you could redirect your screen session, your screen output from the computer in your office to any nearby computer. So you could read emails, or maybe even run a chat program. And the same worked for forwarding telephones. So essentially, your phone number followed you around to the room you're actually sitting in right now. So this was 30 years ago. It was a research project. It worked pretty well, but as you can imagine, it was pretty limited. Now, you had a number of buttons available to trigger some additional events like do not disturb or something like this, but still, it's a one-way communication and it needed lots of infrastructure, so the technology in these badges was pretty simple. A more complex development was again done at Park Xerox Research Labs a couple of years later, so 93, and they invented something they call Park Tap. Park taps are mobile tap-sized devices, as you see on the top right side of the slide. So they already contain a microcontroller, a Motorola 68K series controller, which is running at around 20 megahertz, and it had a lot of RAM, already 4 megabytes, and it also already had an LCD display and a touchscreen input using a unistroke alphabet. So these controllers were not powerful enough to do something like handwriting recognition, which you might be used to for modern tablet devices nowadays, but you had to use very primitive gestures like the ones shown in the middle picture on the right-hand side of the slide. But still, you could input text if you practiced. If you ever used a Palm Pilot PDA, you might recognize that some of these are very similar to the input devices or the input methods used in the Palm PDAs. So this technology is closely related. Now these devices were still communicating using infrared. So on the lower right-hand side, you see a picture of the infrared base station. So again, in every room, you had a base station which was mounted at the ceiling. Now this was bidirectional, so the device could not only send information, it could also receive information like emails or messages. This, of course, because it was based on infrared, had a low bandwidth running on a modulated IR carrier, and the transmission radius was accordingly, because it was infrared, relatively small, so around 7 meters. So enough for an office room, but you needed one of these relatively complex devices in every room. But this now enabled context-aware applications, so you could access information, you could read your email, you could send messages, you could collaborate using these devices. So this was already quite a step forward. Now, a couple of years later, there was a research project at IBM, and they tried to make all this technology quite a bit smaller. So here you can already see an ARM chip in operation, one of the early ARM-based microcontrollers in ARM7, running at between 18 and 74 megahertz. So here you see one of the technologies which will become important in the last part of this course, energy management. So you can scale the frequency of a CPU and accordingly the power consumption according to the tasks it actually has to fulfill. So this is a wristwatch, a bit of a clunky one to be honest, because it was 16 millimeter thick. It weighed like 43 grams, that's okay. And it already had a monochromed LCD and later models, even an OLED display, and it had a number of input devices. So actually this display was a very small touch panel. It had a stem switch, what you call a crown in regular watches, and a number of buttons to control applications. It had even more RAM and flash than the Xerox pad we've seen before. So this IBM Linux smartwatch has 8 megabytes of DRAM and 16 megabytes of flash. And it could already communicate over more advanced protocols, so it already supported the very new Bluetooth back then, but also could fall back to infrared data communication and also a serial communication when you put it into a cradle to charge. You could also exchange data like update your calendars and update your addresses. In addition, you had other devices. So it had a speaker and a microphone, it had a vibrator, a fingerprint sensor, and even already a 2-axis accelerometer. On the lower right-hand side, you see how small the technology had to be to fit in a watch. So it's essentially 3 PCBs, one controlling the battery controls and wireless, one with the CPU and memory, and the third one which contained the small display. And you see the size comparison. I think that's an American quarter. So that's quite small. And still, this was one of the very first prototypes. And if you look at a current smartwatch, well, the functionality won't be too different. The CPUs got faster, the memories got faster. You even got like 4G, 5G communication maybe in there. And of course, a color display, a nice one. But still, this was one of the basic first implementations of making a watch much more than a watch, making it a little computer that is always networked. And with this IBM Watch or WatchPad, you could do very many different applications. So luckily, the IBM Research website is still up, so there's much more information on this available if you're interested. So you could already run personal information management, like storing addresses and messages and so on. It could do gesture recognition. It could also have handwriting input, which was a bit difficult on that small display, to be honest. It could be a controller for other devices. It could run mobile web services or access it. It even had some sort of web browser, so there was a cut-down version of HTML for very small devices called WML. It could run with other devices, so it could actually beam information to the watch's display. It even had a small web browser in text mode, which you can also find on Linux devices now. Linux It could run SIP, so you could run voice over IP. You could add a GPS component. So GPS was a pretty big device 20 years back, so you had to have it separately with a Bluetooth connection, but still you could view the GPS signals. And IBM researchers also imagined it could do mobile payments and store all your passwords. So essentially, all the things you might be used to today were just invented and imagined back then more than 20 years ago. Now, all of this wouldn't be possible without ubiquitous networking. So as we've seen, very many of the prototypes and the early devices used infrared light communication in the 1990s because wireless radio networks weren't really available or affordable. So there's a standard called the IRDA, Infrared Data Association Standard, which used infrared light in the 850 to 900 nanometer spectrum. And of course, as you know, with your television remote control, mostly you require line of sight. And in practice, speeds are pretty low. You could get up to 4 megabits per second, but you had to be very lucky. So very often it was a couple of kilobits per second. So transferring a video or something over this would have been impossible. Now, IRDA was quite an extensive protocol because it was more or less the only thing available back then. So uh, several companies started to add application layer protocols like IR-OBAX for exchanging objects like address cards, or IRCOM for emulating a classical serial interface. So it could, for example, run a modem internet connection over infrared. But since the late 1990s, wireless radio network technology proliferated. And this was enabled by the availability of what we call the ISM radio frequency band. So this is a band available for industrial, scientific, and I think the M stands for military applications actually, but I have to check. So this is a frequency band around 2.4 gigahertz, and that's what not only Wi-Fi, so wireless networks, used with the IEEE 802.11 standard, which was introduced in 97, but also different technologies like, for example, Bluetooth. So Wi-Fi originally was relatively slow for our expectations today. So it ran at 2 megabits per second, but compared to what you could actually achieve with infrared, this was quite fast. And of course, you didn't need line of sight, and you could go much faster, further away from the base station. So it could be in the next room or on the next floor. Of course, now Wi-Fi networks achieve up to 700 megabits per second in the 802.11 AC standard. Because of the 2.4 gigahertz band being overcrowded, very many Wi-Fi manufacturers also use an additional frequency band around 5 gigahertz to avoid interferences and to increase bandwidth. And Wi-Fi nowadays, of course, you use it every day. It's commonly used as a replacement for cabled infranet infrastructures. Around the same time, another protocol came up called Bluetooth, and Bluetooth was made for a different application scenario. So Bluetooth was originally intended to quickly exchange data between fixed and mobile devices, and also to build personal area networks of wireless devices. So compared to Wi-Fi, Bluetooth is short range, usually up to 10 meters in the most commonly used mode, and originally the throughput was also much lower. Now, with the proliferation of mobile devices and battery-driven devices, low-power wireless networking became much more important. So we'll have a complete part about networking. Of course, we go into more details here. So I'll just give some examples here. So there's a standard called IEEE 802.15.4, which is the physical layer standard for protocols such as ZigBee, 6LoWPAN, or Thread. You've probably heard in the context of the IoT. There's also a Bluetooth variant called Bluetooth Low Energy, which is independent of the classic Bluetooth protocol and was originally incompatible. But the most recent standards, I think since Bluetooth 4.1, include both classical Bluetooth and the BLE standard. And of course, we have mobile network infrastructure, starting with the first digital standard, 2G, which was developed by Nokia and Ericsson in Finland. So the GSM standard in 1991, which enabled up to 40 kilobits per second with the edge extension. And of course, today we have 5G networks up to 4 gigabits per second. So we have quite a bit of development also here. And we have recent development like wide range, low throughput networks like LoRaWAN. So LoRaWAN is a proprietary technology for long-range transmissions with very low power consumptions. So it's very slow, up to 27 kilobits per second, but using this approach, you can actually transmit signals over many kilometers. So it might be especially interesting for scenarios like smart cities, where you want communication that doesn't include lots of data to transfer, but you want to be independent of like radio towers and so on, because the range is so big, you only need a central station somewhere for a smaller city. Another important area which is closely related to the IoT are wireless sensor networks. So wireless sensor networks are defined as networks of spatially dispersed and dedicated sensors that monitor and record the physical conditions of the environment and forward the collected data to a central location. So essentially, that means it's today maybe considered a part of the functionality of IoT. So we have sensors distributed somewhere that communicate wirelessly and then communicate with some sort of centralized infrastructure. So you have lots of sensors, for example, for environmental monitoring. So you want to environment the levels of water in an area, and so you put out sensors every couple of meters that might be able to sensor this and send that back, so you can watch scenarios like a flood coming in or something like that quickly. So this is an active research area since the late 1990s, and it has many applications. We've talked about area monitoring. You could use it for healthcare monitoring. You could use it for habitat monitoring. So there were projects attaching wireless sensors to animals to just figure out where the animals are actually moving, so where they are mostly endangered, where they need to be protected, and so on. You can do environmental and earth sensing, for example, for air and water quality. You could put in sensors that alert for forest fires or landslides or earthquakes, volcanic eruptions, and so on. And of course, if you have a large industrial plant, you can also do industrial monitoring, for example, for machine health in large and complex machinery, where you can't just look inside all the time. You can do data logging. You can check buildings for structural health, like bridges and so on. So wireless sensor networks have common characteristics, including that there are significant constraints on power consumption. So the nodes often use batteries or energy harvesting technologies like solar panels. They have to be resilient. So even if one or two of the many sensors fail, or some part of the network infrastructure, wireless sensor networks should be able to handle the failures of nodes and part of the network infrastructure. And nodes might be maybe mobile, like if you attach them to an animal to figure out where that animal is going, then obviously you have to live with a moving target. Uh, Nodes might be maybe heterogeneous depending on the sensors and processing power required, and nodes or the networks might be required to scale because you're adding additional sensors on the fly when you need them. So this is a basic technology. Nowadays, we'll just see it as part of the IoT for our purposes here. And one final important part are cyber-physical systems. So cyber-physical systems, or short CPS, are engineered systems that are built from and depend upon the synergy of computational and physical components. Now that sounds very important. It just means that essentially we're talking about embedded systems that are somehow operating in a physical environment, like mostly a robot, which might come in many different forms, like in the simple forms like a vacuum cleaner robot, or in very complex forms like autonomous cars or planes or boats. So the physical environment is important here. So CPS systems have to be able to sense the physical environment. So your robot has to figure out where a wall is or another obstacle, and it shouldn't run down the stairs, obviously. And well, of course, autonomous cars or planes have much more complex tasks, as you can imagine. And CPS not only sense the environment, but they interact with the environment, so they can move around, or they have some actuators like a robot arm uh, with which they can move things around and so on. So very many of these things are cyber-physical systems here. So the smart grid is considered cyber-physical systems. Autonomous cars, as we've mentioned, medical systems like medical device implants, like insulin pumps, Industrial control systems, all sorts of robots, obviously, automatic pilots for avionics and space applications. And of course, these can form part of the Internet of Things. We can imagine robots being part of your IoT, taking over parts of your tasks, and you can control them remotely, or even just give them remote tasks, as envisioned by Mark Weiser's vision. So the robot should just keep in the background without requiring your attention all the time. So, from my point of view, the Internet of Things merges all these things. So, cyber physical systems and sensor networks and embedded systems and wireless networking technologies. So, we can look for different definitions, and I found that one here. The Internet of Things, or IoT, is a system of interrelated computing devices, mechanical and digital machines, objects, animals, or people that are provided with unique identifiers and the ability to transfer data over a network without requiring human to human or human to computer interaction. So here you see very many principles of ubiquitous computing, of Mark Weiser's ideas coming up again in a much more complex context. So the IoT here definitely builds on previously discussed technologies for embedded cyber physical systems, ubiquitous wireless sensor networks, and so on. Now, one thing we actually haven't discussed is what is the thing? So the first quote above already tells it a bit. It's an interrelated computing device or machine or. And there's another definition from the same source, which says a thing in the Internet of Things can be a person with a heart monitor implant. So there's a computer inside of a human to enable medical supervision or a healthy life for a human. A farm animal with a biochip transponder, so you know where sheep are going. An automobile that has built-in sensors to alert the driver when the tire pressure is low. That's common nowadays in modern cars, obviously, or any other natural or man-made object. And now that's important, that can be assigned an Internet Protocol address and is able to transfer data over a network. So again, data is important here. So very many embedded devices could operate just independently of a network connection. And very many embedded devices do this all the time. Imagine just a simple vending machine, which maybe doesn't need an internet connection, or maybe it does nowadays to alert the person that, it needs to be restocked, right? Now, IoT applications we see include hardware and network, but importantly, it includes data. So both definitions here mention data. So what about the data in the Internet of Things? So is the Internet of Things all about data, like some people think? Well, it's an important part. So they're complex, they're networked, they're heterogeneous, distributed systems. The question is, how can we handle application data? Now, obviously, since this is application data, it's very much dependent on your specific application, what this data is all about. Nevertheless, for building interoperable systems with heterogeneous components, we need to have some standards. And these standards are defined in network protocols on different layers. So you've probably seen the ISO model of network layers, and something similar happens here. So essentially, we can classify protocols for the IoT into the network protocols we use, so the data link and physical layers. And then on top of these, we have the IoT data protocols, which would be on the presentation and application layers of the ISO stack. So IoT data protocols are usually used to connect low-power IoT devices, so they provide communication with hardware on the user side. And on the data protocol side, we have things like MQTT, so the message queuing telemetry transport. So this is a published subscriber messaging model, which enables simple data flow between heterogeneous different devices. And there are other protocols like COAP, Constrained Application Protocol, which is an application layer protocol for IoT systems, which are based on the web HTTP Internet Transfer Protocol. There's also a protocol called AMQP, the Advanced Message Queuing Protocol, which is, again, an application layer protocol, and there you can define transactions, so which can either be completed or they have to be restarted from scratch, and this is usually used between servers. We'll talk about networking protocols for the IoT in the respective part of our course later in much more detail. Now, if you look at press articles about the IoT, there is always a connection made, or very often a connection made now to artificial intelligence. So artificial intelligence really is very often discussed as a technology that complements and extends the capabilities of IoT applications. Now, what does artificial intelligence mean? Well, we could talk a whole semester about this and not come to a conclusion. So I've just copied a picture from a paper on AI and the IoT here. So essentially, AI in these contexts mostly means machine learning, so neural networks here. So neural networks are a very sophisticated form of pattern matching. So, for example, you would be able to identify traffic signs not only as a human, but you would enable your car running a neural network to identify traffic signs that indicate speed or stop sign and so on with a high probability. So, these AI technologies are not new. They have been invented in the 70s and 80s, especially these neural networks for learning, and they have recently uh, seen a renaissance through these deep learning neural networks, which enable the user to use many more layers of these networks than before. So, combined with the higher computing power enabled by Moore's law, these AI approaches actually enable neural networks to perform much more sophisticated tasks than before. And they're also part of all these modern technologies like autonomous cars and so on. So it can support complex tasks such as machine vision and speech recognition. Obviously, these are important for interaction with humans, interaction with the physical environment. Now, the problem with all these AI solutions is they usually require significant computational power. So, the solution that was used early on and is mostly used today is that this computational power is actually not available on the end user devices like on your mobile phone, but it's available in the network infrastructure, so somewhere in the cloud. So when you ask your Alexa speaker to tell you the weather, it's not recognizing your words on the local device usually, but it's sending the audio samples to a server somewhere, and then some machine learning application is running, transferring it into maybe human readable text, so ASCII text, and then this text is parsed and it figures out, oh yeah, you want to know the weather, it gets your location, and then it uses an internet service to transmit the information about the weather back. But more and more, there's edge computing, what we call it today. So, edge computing means that this functionality is now executed on the end user device or on a device somewhere at the end of the network instead of in the cloud. So, for example, on your mobile phone, which could do speech recognition, or for example, in an autonomous car, where there's just not enough bandwidth available and the latencies are far too big to process like the video data from all the cameras in your car somewhere in the cloud. So AI might become an important part. We're going to discuss a bit about this. This is a recent development, so I would say keep your eyes open for AI developments in the IoT. So when we talk about IoT, of course, we have to talk about where IoT is actually used. And this is a nice overview I found about the top 10 IoT application areas from almost 2 years ago. And what's interesting here is actually that IoT has much more significance in areas where we don't expect it right away. So all these applications like smart buildings and smart homes, they only make up a very small part of the IoT application market. So it's on place number 9, these buildings with like 3%. And you have agriculture, supply chain management, so all sorts of logistics like following where your parcels are going. Healthcare is a more important part and getting more and more important, obviously, as people are getting older and with all the pandemics going on right now. You have smart cities, which are quite an important part, but then you have retail applications, which might include logistics, but especially also consumer facing retail in stores. You have energy networking, which is something you usually don't see. Then you have transportation mobility, and the top part with almost a quarter of the global share of IoT projects is actually in manufacturing and industrial applications. So In the next lectures, in this first part of the course, we'll give an overview of some of the applications, talk about typical applications, and we'll also provide some videos and additional material to give you an insight into how and where IoT can be used for all these areas. So, what's the difficulty when building IoT systems? What are the major challenges when we're, as a developer, building, developing, deploying IoT systems? Now, one thing is you have so many different devices and they all have to talk to each other. So we have to enable interoperability. There's many different protocols on all layers. We have to enable reliable communication. We have to enable communication that works between devices with low computing power and high computing power. So this is already quite complex. For all the mobile and battery-driven parts, we have to enable energy efficiency, so we have to be able to build low-power devices, but we also have to enable our applications to save energy. So there's much data running around in IoT networks, and some of this data might be critical, like your personal healthcare data. You don't want everyone to read the state of your heart right now. But also, of course, like banking information, whatever you can imagine. So security and privacy are many are very important components of an IoT design. And the common joke is the S in IoT stands for security. So security in many IoT applications is severely lacking. So this is a point we're going to discuss in detail later in this course. Another problem is support and longevity. So essentially, very many electronic devices are, only running for a few years and then there's no support. So you can't get spare parts anymore. You can't get software updates related to security or functionality. And very many manufacturers also build devices with so-called planned obsolescence. So this means that your device will fail after a couple of years, so you have to buy a new one. It's not repairable, so you create more and more e-waste. You have to produce new devices, which contribute to CO2 emissions again. So in the end, this is a big problem, especially with billions and billions of devices out there. Another problem is that devices like cars have a long lifetime. So maybe you want to use a car for 15 or 20 years, or somebody else wants to use it, even if you don't want to use your old car anymore. So your electronic components are usually not manufactured for this time span. So a microcontroller might be manufactured for 5 years, and if you get really lucky, you get long-term contracts for 10 years. But if you need a spare part for your ECU in your car like 20 years later, you either have to store all these pieces or you have to find a plan to replace it with something more recent, which is difficult because you have to go through all levels of certification again and so on. So the lifetime of electronic components, especially complex ones like microcontrollers, and also the software on top of it, is very much constrained compared to the expected device lifetime for more complex and expensive applications. And cars are not the longest example. So planes usually are used for 50 years. Maybe industrial devices in manufacturing plants that cost millions and millions are used for even longer times. And a special problem for IoT devices based on internet protocols running on the IPv4 protocol is that the world has run out of IPv4 addresses. Back when the internet was invented with only 4 nodes, 4 billion possible addresses seemed like a lot. Now we have many more devices out there, so we can't afford to give each of these devices its own IPv4 address. So there was a new standard introduced also in the mid-late 1990s called IPv6, which enables for 128-bit addresses. So you can address, I think, every atom in the solar system, which should be enough for quite some time. But amazingly, the adoption of IPv6 is still slow. Maybe the IoT is actually much faster here because there's just an urgent requirement to address that many devices here compared to your PCs and phones and notebooks. So as we've seen, the IoT has so many devices, and we can model the IoT. So this is taken from the IoT World Forum, a so-called reference model. And this is, as you know, can imagine very similar to standard network stacks, but it includes more. So it starts on physical devices and controllers, so the things in the IoT. Then we have to talk about the networks, the connectivity, so communication. On level 3, there's edge computing. So how do we handle data on the edge? How do we transform data on the edge, filter it, encrypt it? We have to transmit and accumulate data somewhere. We have to aggregate data. And of course, then we have applications like reporting, analytics, control. And finally, on top, there might be some humans who are actually the beneficiaries of this application. So we have collaborations, we have processes. So on the highest level, we're going to involve people or business processes that rely on all these layers below, and information has to travel up and down across these 7 levels in the IoT. And we're going into details about this in the upcoming lectures in this course. So, defining what the IoT is perhaps the most difficult question, and we're not going to solve it completely in this course because everyone has a different idea, different expectations and constraints, and of course, different applications and use cases. So in this course, I want to give you an insight of the most relevant areas of IoT technologies. So we're talking about applications, about the infrastructure, about data management, about privacy and security, and finally about energy efficiency. In this context, I'm going to provide you with real-world examples and use cases through case studies and also interviews. And for those of you who are taking the complete course, DV8070, you're also expected to get some hands-on experience. We're using an IoT application project, and we're going to discuss this in the next week. So details about this. So we're going to provide an example platform if you want one provided for you, or if you have a platform you're already working with, you're familiar with, and you have an idea for an application, feel free to propose it. But we're going to talk about this in one of the upcoming live sessions. So in this course, we're going to talk first about the application areas. So all of these 5 parts are included in the complete course, or as you noticed, you could register for some of the parts of this course separately. So the first part is concerning application areas. So we're discussing applications, challenges, and interesting requirements for several of these areas here. The second part is about infrastructures, so from hardware to system level software. Part 3 is about data management, so collection, storage, processing, analysis, automation, and presentation of data. Part 4 then concerns privacy and security, so surveillance, behavioral patterns, but also encryption, how to do secure firmware updates, what are the attack vectors on IoT, and of course also interesting examples here. And part 5, finally, is concerned with energy optimization. So, for example, how can we achieve 10 years of battery life for a device? What is influencing energy consumption? And of course, how can we minimize this? So stay tuned. The next lecture is going to come this week, and we'll also schedule a live session whenever I have figured out when exactly we can find some schedules that work for most of us. So here's some references if you want to dig deeper. So number 1 is the original visionary paper by Mark Weiser, The Computer for the 21st Century, about defining pervasive computing. The second one is a paper about the active badge location system by AT&T and Olivetti. And the third one is a Park tab by Xerox PARC. The fourth one is one of the many papers about IBM's Linux Watch, so there's many more if you want to look at this, and the webpage is linked on one of the previous slides. Number 5 is our textbook on embedded system design as foundation for cyber physical systems and especially the IoT, which is open access, so you can download it in PDF or in EPUB format and read it. So this is a very interesting textbook giving much more background than we can do in this course. Number 6 is the COM technology paper by Mark Weiser, again going a bit deeper into their vision a couple of years later. Number 7 talks about IoT and sensors, so smart environment monitoring systems. Number 8 is a link to the IoT agenda, trying to define what IoT actually is. Number 9 gives a bit of a historical vision. This is already 10 years old, but it shows the progression from networked computers to networked things, which is quite interesting. So Friedemann Matern in Zurich was one of the persons very much involved in sensor networks and then later on IoT definitions. And finally, number 10 then gives a link between artificial intelligence, edge computing, and IoT. So there's lots of stuff to read. You don't have to read these literature references, obviously, but if you want to dig deeper, you're welcome and feel free to ask questions about this. So that's all for today's lecture. Thanks for listening, and until next time. Bye.